Yes, children. Let us start with the next property, that is electronegativity. So what is electronegativity? It is the ability of an atom in a compound to attract a shared pair of electrons. Now see here, in the case of HCl, hydrogen is having 1 electron and chlorine is having 7 valence electrons, and 1 electron of chlorine is being shared between hydrogen and chlorine. And you know very well that chlorine is more electronegative than hydrogen. Why it is more electronegative? Because it's having 7 protons, so it is having a stronger tendency to pull an electron from the atom with which it is combined. Hydrogen is having just 1 proton, is it not? So the nucleus of chlorine is much stronger, so it can pull the electron, or it can attract the electron much more. That is why the pair of electron between hydrogen and Cl will be more towards chlorine. Okay, like it will be hydrogen and Cl. See, the electron of hydrogen is more towards chlorine than towards hydrogen. So this is the ability of chlorine to pull the shared pair of electron towards itself. Now this electronegativity is not a measurable quantity because it depends on the atom with which it is bound. Okay, so you cannot say exactly this is the, you don't have any sort of value for that. Still, Linus Pauling in the year 1922, he assigned arbitrary values for different atoms for electronegativity, and he assigned a value of 4 to fluorine, that is the highest value. Now, this property you already know it. Electronegativity increases across a period as the non-metallic character increases, and electronegativity, it decreases down the group as the metallic character increases. Down the group metallic character increases, across the period non-metallic character increases. So electronegativity is a property of a non-metal basically. Okay, so this particular property you already know it. Now, what is the difference between oxidation state and valency? See, valency is the property of an isolated atom. Okay, that is, an atom, if it is having say 2 valence electrons, it has the capacity to lose 2 electrons. So valency of that atom, you consider it as 2, right? But what is oxidation state? It is the charge possessed by an atom relative to the atom to which it is bound. Okay, so I have given you an example here, OF2. In this, O has plus 2 charge, F has minus 1 into 2 is minus 2. So the charge on oxygen should be equal and opposite to that. So O will have plus 2. Whereas in this compound, that is Na2O, the charge on oxygen is minus 2. Na is having plus 1 into 2 is plus 2. So O will have a charge equal to that of plus 2, that is minus 2. Equal and opposite to the charge on Na. Okay? So this will have here minus 2. See, in this, the oxygen is having a different charge, and this, the oxygen is having a different charge, and this is what you call it as oxidation state. But as such, you consider what is the valency of oxygen. Valency of oxygen is always 2 because it has the capacity to gain 2 electrons. So that is what you call it as valency. Valency is the tendency of an atom to gain or lose electrons to attain octet configuration. But oxidation state is the charge possessed by an atom in the combined state. Okay, so this is what you have to remember. Now, let us see more about this electronegativity and another property called electron gain enthalpy. Just like ionization enthalpy, electron gain enthalpy is also another property. Now the process of gaining an electron, it may be both exothermic as well as endothermic. Now in the case of fluorine, if it gains an electron, it is releasing 328 kilojoule of energy. And energy released is exothermic, you know it. And for exothermic reactions, delta H is always denoted with a negative charge. This also you know it, thermodynamics you have done. So delta H Eg, that is electron gain enthalpy, is negative. For exothermic reaction, delta H is negative and the reaction is said to be spontaneous. Right? Any exothermic reaction is generally spontaneous. Now supposing if you want a neon atom to gain an electron, will it gain? No, because it is already having completely filled electronic configuration. So it would not prefer to gain an electron. Now when it does not taking an electron spontaneously itself, what you do? You supply some energy, force the atom to take up an electron. So in this case, it is endothermic and the reaction is non-spontaneous. It is not spontaneous. And for such reactions, delta H is found to be positive. Okay. So if energy is released, delta H is negative, and if energy is supplied, delta H is positive. So for endothermic reaction, delta H is positive and the reaction is non-spontaneous. And what about noble gases? Noble gases have positive electron gain enthalpy. Just like this neon I have shown, neon is a noble gas. So in general, if you consider noble gases, they have positive electron gain enthalpy because they already have stable electronic configuration. There is no need to gain an electron. Okay, now F is gaining an electron to become F minus and it is releasing 328 kilojoule of energy, and Cl is also gaining an electron to become Cl minus and that is releasing 349 kilojoule of energy. Now you know very well that fluorine is much more electronegative than chlorine. So the spontaneity of fluorine is much more than that of chlorine. This is what you expect. But the amount of energy released in the case of fluorine is less than that of chlorine. Now why so? Now you also know that greater the energy released, more favorable the reaction is. So that means Cl grabs an electron much more readily than that of fluorine. This is what is understood from this equation. But then what is the reason? Still we say that fluorine is the most electronegative element. On what basis? In spite of releasing lesser energy than chlorine, still fluorine is considered the most electronegative. Why? That is because in the case of fluorine, the electronic configuration is 2,7 and in the case of chlorine, it is 2,8,7. Now this electron will go to the third shell and this electron will go to the second shell. Now when the electron is going to the second shell, then the incoming electron will experience more repulsions from the existing electrons. So because of the repulsive forces, what happens is net energy released is less. That is, the atom must have used up some of its energy. Though it wants to release more, it has used up some of its energy in order to balance the repulsive forces or in order to neutralize the repulsive forces between the incoming electron and the existing electrons. Since it has used up a little, the net energy released is less. But in the case of chlorine, the repulsions are less because the size is big and the electron is moving to third shell. So because of the bigger size of chlorine, the electron-electron repulsions are lesser because these electrons are in a much bigger space. So the incoming electron is not facing that much of repulsion what is happening in the case of fluorine. That is why the amount of energy released is more. Whereas here some energy has been utilized, so energy released is less. Okay. So that is what I have given you here. Chlorine releases more energy. This is because of the small size of fluorine and greater interelectronic repulsions that the added electron faces. Net energy released is less in the case of fluorine, and so you say delta H Eg of fluorine is less negative. Minus 328 is less negative than minus 349. Same way, in the case of oxygen and sulfur also, same thing happens. Now oxygen is releasing, by taking up an electron, 141 kilojoule. Sulfur is releasing, by taking one electron, it is releasing 200 kilojoule of energy. Again, you know very well that oxygen is more electronegative than sulfur. In spite of that, energy released in the case of sulfur is greater than that of oxygen. Now same reason here also, the electron is going to a smaller sized atom, so this will face much more repulsions than this electron, which will go to the third shell. Here it is 286, here it is 26. So the repulsions are less because of bigger size, and hence the amount of energy released is more. But here, of course, the spontaneity is much greater, but some energy is utilized to overcome the repulsive forces between the incoming electron and the existing electron. Hence, net energy released is less. Okay, small size and high interelectronic repulsions. So, net energy released is less, or some energy is utilized in overcoming the electron-electron repulsions. In the case of oxygen, the second electron gain enthalpy is positive. Now, what do you mean by second electron gain enthalpy? O plus electron becoming O minus, and the amount of energy released is 141. This is your first electron gain enthalpy. Now this O minus is taking up another electron to become O2 minus. This is the amount of energy associated in this reaction is called as second ionization enthalpy. Right? Now here the second electron gain enthalpy is positive. Why? Because this is already a negatively charged species and an electron has to be added. So there will be more and more of repulsions between the two. Hence the amount of energy released is much less. Or you can say even this requires energy, but overall energy will be exothermic. It will be in the form of negative delta H. Okay, now what are the factors on which this delta H Eg depends? Atomic size. As size increases, distance from the nucleus increases, force of attraction of nucleus for the added electron decreases, and hence delta H Eg becomes less negative, or energy released is less. Then is nuclear charge. As the nuclear charge increases, force of attraction for the added electron increases, energy released is more because spontaneity is more. So delta H Eg is more negative. And apart from that, there is another reason, that is electronic configuration. If the atom has half-filled or fully filled configuration, it will not gain an electron. So energy is supplied in such a case to add that extra electron. So in that case, delta H Eg will be positive. Like in the case of noble gases we saw, it is having positive electron gain enthalpy. Right.